Welcome to Brain Vision.
In this problem, we're going to talk about Compton effect. So consider that we have a photon that has a wavelength lambda that strikes an electron originally at rest, and after the collision, the photon loses some energy, so it has a new wavelength lambda prime, and the electron gains some kinetic energy and has a final speed equal to v. And Compton effect also tells us that lambda prime is equal to lambda plus h over c over mc, I'm sorry, times 1 minus the cosine of this photon scattering angle theta. And here h is Planck's constant, m is the mass of the electron, and c is the speed of light. Also, we're going to need to remember that the kinetic energy of a massive particle is equal to the mass of the particle times c squared times gamma minus 1, where gamma is 1 over the square root of 1 minus v squared over c squared. Okay, and finally, the energy of a photon is equal to hc over its wavelength. And in question A, we have to find an expression for lambda as a function of lambda prime and v, given the situation that we have up here in this drawing. So notice that we can do that by applying conservation of energy. Notice that the initial energy of the system is hc divided by lambda. There's also the rest energy of the electron, but I'm not going to worry about that because it's going to appear on both sides of the equation. So it's just going to cancel out anyway. I'm not going to bother writing it. And this is equal to hc divided by lambda prime. This is the final energy of the photon plus the kinetic energy of the electron, and that is mc squared gamma minus 1. So my goal here is to isolate lambda, so I'm going to invert. So I have lambda over hc is equal to 1 over hc times 1 over lambda prime plus mc squared over hc gamma minus 1. The hc's cancel out, the c's here do as well. I'm going to multiply everything by lambda prime and divide by lambda prime, such that we obtain that lambda is equal to lambda prime divided by 1 plus mc over h times gamma minus 1. So this is our expression. Then in question B, we have to find theta as a function of lambda and lambda prime. Notice that the formula that I wrote up here, the Compton effect formula, works for special relativity as well. So even for relativistic scenarios, this formula holds. So I can just use it and isolate theta. So we have that lambda prime is equal to lambda plus h over mc times 1 minus cosine of theta. So lambda prime minus lambda is equal to h over mc times 1 minus cosine of theta. So lambda prime minus lambda mc over h is equal to 1 minus cosine of theta. I'm going to isolate the cosine of theta. So we have cosine of theta is 1 minus mc over h lambda prime minus lambda. This means that that theta is equal to the arc cosine of 1 minus mc over h lambda prime minus lambda. Okay, this is the answer to question B. Then in question C, we have to evaluate both lambda and theta that we found in question A and in question B, considering that lambda prime, the wavelength of the outgoing photon, is 5.1 times 10 to the minus 3 nanometers. V is equal to 1.8 times 10 to the 8th meters per second. So lambda, remember that it's equal to lambda prime divided by 1 plus uh, lambda prime. And actually up here I forgot to write a lambda prime. I'm sorry for that. I should have written it before. MC over h times times gamma minus 1. Now lambda prime is 5.1 times 10 to the minus 3 nanometers, that's 1 picometer, divided by 1 plus 5.1 picometers, divided by h over mc. It's worth remembering that h over mc is 2.43 picometers. Then we multiply it by 1 over the square root of 1 minus v. That's 1.8 times 10 to the 8th divided by 3 times 10 to the 8th squared divided minus 1. So lambda is equal to 3.34 times 10 to the minus 3 nanometers, or 3.34 picometers. And then we can find theta. So theta is the arc cosine of 1 minus mc over h, that's 1 over 2.43 picometers, times lambda prime, which is 5.1 picometers, minus lambda, that's 3.34 picometers. So theta is equal to 74 degrees, which is the answer to our exercise.